seminar. I use TH such that it's not too much theory. Okay? We're glad to have our own Professor Jiunn-Wei Chen today. Professor Chen received his PhD from Washington, Seattle in 1999, and then spent 3 years at Maryland University, and then 1 year at MIT before returning to NTU. I can even remember when we were talking about the appointment, I myself was impressed by the diversity of Professor Chen's repertoire, and that he can collaborate with many different people. So, yeah. Okay, I'll reserve that joke. I almost just kind of just, with your allowance, I'll still okay. So he returned in 2003 and rose through the ranks and became full professor in 2009. And since I couldn't find his CV, I always want to show off my short-term memory, but I couldn't. I think he received a Wigner Prize at some point, right? And maybe also an academic cynic. No? Okay. But currently he's the deputy director of the COSPA Center. Today, the title is out there. I think the best introduction is that this will be a very quantum gay talk. No, just joking. If you get it, you get it. If you don't, it's Mr. Barry. Oh, you reversed it. Okay. How was announced was, yeah, Mr. Wigner meets with Mr. Barry.
That's an announcement.
Now there's a reversal, so we'll see what happens. Okay, very much.
All right, thank you. So this is a work in collaboration with Xi Pu, who is a postdoc at NTU. He's here now today, and Queen Wang is a professor from USCT from Hefei, and Xinlian Wang is a professor from Berkeley Lab, and he's in Wuhan now. He spent half of his time in Wuhan, between Wuhan and Berkeley Lab. So this is a story about the interplay between different fields of physics, and it starts with a very old subject, which is hydrodynamics. So suppose we have a liquid or a gas system. It is not in thermal equilibrium, but close. Say it's in local thermal equilibrium. Then if we are only interested in the long wavelength physics, here long means it's long compared with the mean free path. Then the system, the physics of the system is governed by hydrodynamics. The equations of hydrodynamics is very simple. You just have the energy momentum conservation equation and the current conservation. You've got one current conservation for each conserved charge. So T mu nu is the energy momentum tensor. Mu and nu goes from 0 to 3. It's a 3+1 dimensional system. And we can write down or parameterize T mu nu and the current with these expressions in terms of energy density, pressure, fall velocity, and the number density. Here we have, in this example, with one just conserved current, we got 5 equations with 4 coming from here and 1 from here. Or we got 6 unknowns with epsilon, with energy density, pressure, and number density, and also 3 components from the fall velocity. It satisfies some normalization, so we got 6 unknowns. So we need one input, which is called equational state, which relates those 3 quantities. Then we can solve them. If we assign the initial conditions, then we can solve the differential equations, the first order differential equations, without problem. And one can add higher degree terms into T mu nu and J mu. But since we don't have more equations to constrain them, those will be inputs in the problem. Those prefactors of those higher degree terms are called transport coefficients, like shear and bubble viscosities and conductivity and so on. Those are inputs in the theory. Although the hydrodynamical equations are simple, but we know it cannot be the whole story because if the system has massless fermions, then it could happen that when we turn down interactions, a left-handed fermion, say spin 1/2 fermion, could turn into a right-handed one if there is interaction. In a free system, a left-handed fermion will stay to be left-handed. But when we turn on interactions, this might not be the case. Here, if we turn on the mass, then a left-handed fermion will turn into a right-handed fermion. But I'm talking about massless fermions. And this is in this talk, you only need to know this is a purely quantum mechanical effect. And there is an interest to see this microscopic quantum effect in a microscopic hydrodynamics. Let me give you some example. BEC, Bose-Einstein condensation. If you can experimentally demonstrate this kind of quantum effect and see it in a microscopic co-atomic cloud, then you deserve a Nobel Prize. Actually, 2 Nobel Prizes have been awarded to co-atoms. And also, Schrödinger's cat. If you can make a cat which is much bigger than an atom, then even though the cat is much smaller than the real cat, then you can still get a Nobel Prize, which was awarded recently. So there's an interest here. The question is, how? To incorporate axial anomaly into hydrodynamics, we know that we can modify the hydrodynamic equations into this form. The energy mobility tensor would have some source term coming from the work done by the electric field. So this is just the acceleration of the electric field to charged particles. You still have current conservation. This is a vector current, which is the number of left-handed plus right-handed particles. So total number is still conserved, even though you turn a right-handed particle into a left-handed one. But the difference between the left and right, called axial current, is no longer conserved because you turn a left to a right-handed particle. And the rate of this kind of transformation is proportional to E dot B. E is the E field, and B is just the usual B field. Here I'm using the 4-vector notation, but if you go into the flame where the fluid is at rest, say locally at rest, then it's just the usual 3-vector B field and E field. Also, I want to define a vorticity. Also in this frame where the fluid velocity is 0, it is just a curl of the velocity. So this is called vorticity, and this is the B field and E field. So we know we got to have this kind of equations coming from quantum field theory, say just massless electrons in background electromagnetic field.
The massless electron QED is well defined here?
Yeah. What do you mean? You're concerning about asymptotic freedom, or?
No, because QED, well, not only that QED as we know it is massive, so this is not a physical case.
No, this is not a physical case. Yeah.
But I'm asking whether it's so consistent, because you have EM field, and the EM field is dynamical, right?
No,
So-
it's just a static background.
Static
background, right?
Okay, static, no, but even static, you have stored energy in the EM field.
That's right.
So it can create electron-positron pairs, which are massless. So what's the dynamical system?
Good question. That part was not included here. So
you disallow the pair creation. So it's the electron. What is the electron?
it doesn't. Even you have pair creations, those equations will still be satisfied. I'm talking about current conservation, things like that. When you create a pair, then you still have current conservation, and actually this is also satisfied.
But I don't know what that theory is.
Okay, so the starting point is that you have a system that looks like a fluid, and that requires some condition like a turning-on interaction and wait for a long time, and you can ask whether that condition, like near thermal equilibrium, can be reached in this case.
The electron and positron are massless, but what is the positronium mass?
Positronium, you are thinking about the bound state, right?
We started out with massless, so there's no mass scale.
Okay.
And what is the photon?
All right. So I can tune the external E field and B field to be infinitesimally small. So the effect that you are talking about can be infinitesimally small and hopefully can be neglected.
Okay, I'll let you go on, but my question is whether this whole starting point is so consistent.
Okay.
You see, in QCD is not a problem.
Mm-hmm. So you think QCD is okay, but QED you worry about it.
Well, QED, there's a short distance problem. QCD does not have a short distance problem.
Okay, so it's entirely free then, right?
Yeah, right.
All right, so let's bypass that first. So for the axial current, from parity alone, it does not forbid us to add those two terms. One is proportional to the B field, one is proportional to the vorticity, because those two are axial vectors, and so is the axial vector current. So parity alone does not say that those two terms are not allowed. However, you don't see those two terms in Landau and Lichu's book of hydrodynamics. And since Landau seldom made mistakes, really, so you kind of worry that whether there's a reason that those two terms were not there. And so Stem-Sung went into check the second law of thermodynamics, which says that the entropy production in the process should be always non-negative. And it turned out that kind of current, if you add in, it seems to violate the second law of thermodynamics. So it seems to provide a reason that why Landau didn't put those in. However, there are some explicit calculations showing that you get non-zero transport coefficients for those vorticity effect. And those are calculations done for specific quantum field theories. Those are strongly interacting, and those are super Yang-Mills theory, but it is planned to be a direct computation of those effects. So the computation is performed by assuming this correspondence is correct. This is the ADS-CTP correspondence. It says that if we are interested in a four-dimensional, that means 3 plus 1 dimensional, one dimensional time, 3-dimensional space, gauge field theory, which is supersymmetric, is super Yang-Mills actually. And then the theory would be equivalent to a 10-dimensional string theory in a 5-dimensional ADS background cross 5-dimensional sphere. ADS space means that it is a gravitational space with a negative cosmological constant. And so it says that the two theories are equivalent to each other. It's called holography because the field theory is living at the boundary of the ADS5. But the nice thing about this correspondence is that it's a strong-weak duality. So if you are interested in a strongly interacting super Yang-Mills theory, it's a specific super Yang-Mills theory, then you can just work with the weakly interacting string theory, or in some limit, it's just a gravitational theory. So you can perform the computation and learn about the strongly interacting theory, which is usually hard to handle. So, and this correspondence has passed lots of non-trivial tests, even though probably you cannot claim that there's a proof, but it passed lots of tests, non-trivial tests, and you can even claim that if there's a because this correspondence is so dramatic, if there is something wrong, then you should you should see things to go wrong very quickly, but in lots of aspects, it seems to be fine. So within this framework, two groups set up independent equations and reached the same conclusion that the vorticity current, the current induced by vorticity, is allowed. The first calculation is set up by the Milwala and Loris group. They are interested in a super Yang-Mills plasma living in the 3 sphere. And the corresponding gravitational setup is a rotating black hole. And another calculation is with a charged black hole, such that when you have black hole, you got finite temperature, and if it is charged, then you got finite chemical potential. And you put in the Chern-Simons term in the 5-dimensional theory, so at 4-dimensional theory, you got the anomaly effect. And so both calculations seem to indicate that a non-zero vorticity, chiral vorticity effect can be obtained. And so this made Sun and Soroka went back to check whether Sun's previous second law thermodynamics calculation is flawed. So they found out that if they generalize the definition of the entropy current by adding two terms, one is proportional to B field, one is proportional to vorticity, then the second law of thermodynamics can be satisfied. Furthermore, they relate those two transport coefficients, and they are all proportional to the strength of the anomaly. And so this is a nice story to tell you that a good example to tell you that ADS-CFT is actually used for physical systems. Yeah, it's not just good for some theories that you will never see in nature. So in hydrodynamics, those transport coefficients are input parameters. It would be nice to have more prediction power if you can have if you can compute from microscopic theory and get those macroscopic quantities, those transport coefficients. And this is what kinetic theory can do for you. A kinetic theory generally describes lots of particles, and each particle has a position in the phase space. Then you just describe how each particle moves in the phase space. Usually you describe it as a density or some distribution. So a kinetic theory would describe a small volume in phase space and how it moves in time. And how particles move in and out of the phase space through collisions. A specific example is the Boltzmann equation, which describes the time evolution of the particle number distribution in the phase space, meaning that in the X and P space. And this is a semi-classical approach, because you know if you talk about X and P at the same time, then it cannot be fully quantum mechanical. So in this approach, particle collisions are described quantum mechanically, but after collision, particle will move and until it collides with the other particle. So the moving between collisions is described classically. So in this is semi-classical approach. However, in weakly coupled in the weakly coupled limit, weak coupling limit, this approach in some cases can be shown to be equivalent to computation of it's called Kubo's formula. So it is equivalent to some fully quantum field theoretical calculations in the weak coupling limit. Okay. So in this kinetic theory, an important ingredient is particle number conservation, because you keep track of particles by imposing particle number conservation in the collision. Okay. However, in the theory with anomaly, particle number is not conserved. A right-handed particle can turn into a left-handed particle. So we don't have this in a chiral theory.
Quick question.
Yes.
So your so-called microscope theory is the massless QED, as you said
Yes.
at the beginning, right? So
That's
the
right.
underlying microscope theory is massless QED.
Yes.
And so as you wrote before, the divergence of T mu mu, divergence of J mu, divergence of J phi mu
Right.
are given, right? So they
That's
are
right.
they are derived from massless QED.
That's right.
Okay. So the goal is what? So what's the goal?
The goal is to construct a kinetic theory that you can compute everything.
But presumably CCB are known from QED,
No.
right? No?
No, that part in the hydrodynamics, those are non-parameters.
And but So
those
you
are
trying to
parameterized in
relate
hydro.
C and C of D and DB to the coefficient.
That's right.
To C, for example, to the anomaly coefficient.
That's right.
So you have 4 parameters.
That's right.
In the macroscopic hydrodynamics theory.
Right.
And you would like to relate these 4 parameters to C.
That's right. So,
I see. Okay.
so what we got to figure out the prefactors. We know it's proportional to 1 factor of C, but the prefactors and
so you need to calculate the proportional coefficient.
That's right.
I see. And the next the last one. Okay. The particle number is just it's not the particle is conserved, right? So this,
That's
the
right.
chirality is not conserved.
That's right.
Okay.
Right. The sum of left plus right-handed particles are
Yeah.
conserved, but not left or right individually. So there's
so
a
presumably there's no mystery, right? No any mismatch. It's just that you derive something from microscopic input, and
that's right.
the mission is just to do it.
That's right. Right. But this is non-trivial, as I said.
Oh, okay.
So the question is how would you do it? Yeah, it's a non-trivial task. So in this interesting paper by Pushi, who is here, and his collaborators in their PRL, they started from the quantity called Wigner function. It is actually very close. It's a fermion bilinear. So if you put the sidebar and the side at the same point, then this is similar to a local current. Now I just smear it into a non-local form, but you put a so-called gauge link such that the whole thing is gauge invariant. Then you do Fourier transform to the relative distance of the two. So at the end, it looks like it depends on, this operator depends on x and p at the same time. So it looks like a distribution in the, so the matrix element of this operator looks like a distribution in the phase space. So this is the operator. And the operator satisfies this first order differential equation coming from the requirement that the Dirac equation of motion for the Dirac equation is satisfied. So this is the first order differential equation. And here it is gauge invariant, so it's in terms of F min nu, not a gauge field. And then we can just project out the vector and SU vector components. And if we integrate out the momentum, and over here we can see that if we integrate out the relative momentum P, then we get a data function here. We end up with a local operator. So we can recover the vector and SU vector current. And in this approach, so why do you start from, why do you take this as a good starting point? It turns out that if you look at the derivation of axial anomaly, say think about triangle diagram, it's actually coming from the subtlety of the ultraviolet divergence, ultraviolet physics. And so one way to deal with this is to properly impose some regulators to regularize the ultraviolet divergence and make it to be finite. And then after you complete the whole calculation, and then you can take the cutoff to infinity, and you've got the final result. And one way to implement the UV cutoff is to smell the local operator into non-local. This is done in Peskin and Shorter's textbook. So you can take a look. And so the point is that since this is a non-local form already, the smelling is done. So it sort of can take, so this takes into account some sort of ultraviolet divergence. This here has no ultraviolet divergence coming from the triangle diagram. So this allows you to get the correct result for Navi. And since we are interested in the physics of anomaly, which is topological, this slide is for experts. So we are going to take the limit where the fermions only interact with the background electromagnetic field, while the fermions can also interact with each other, but we can say the coupling is infinitesimally small. We can take this limit because the result we are interested in is still finite in this case. You can sort of understand this by thinking about, say, the triangle anomaly effect is actually a topological effect. So quantum loop corrections actually doesn't change the lowest order result. So this has similar flavor. The leading order, well, we can take this limit and the result doesn't disappear under this limit. And it's much simpler to deal with do the computation in this limit. And we are going to take a static limit, and we are interested in long wavelength physics, so we can take derivative expansion, the derivative of derivative in space-time, so the derivative and E and B has one derivative on the gauge field, so they are counted as one derivative order. And we can, so at the 0th order, that means that there's no derivative, then it's just in thermal equilibrium, and we claim that we know what the physics is, so we match it to a kinetic theory, which is just contains particles in thermal equilibrium with the Dirac distribution, for example. And then we can solve the system order by order in the derivative expansion, because when you look at the operator equation, the Wigner function operator got to satisfy, it relates a non-derivative term with the derivative terms, then you can solve it order by iteration. So this is just some technical details. But the result is actually kind of interesting. First of all, you can reproduce the correct hydrodynamic equations. So this is important. And also one can compute those transport coefficients. For example, the current, it can be related to the B field and the vorticity, and so is the axial current. And those transport coefficients can be computed in terms of the mu and mu 5. Here we have set the electric charge to be 1 already. And you can understand, and then the mu 5 is just the chemical potential difference between the left and right-handed particles. Even though the left-handed particles and right-handed particles are not conserved, but at the 0th order they are conserved because the breaking effect is high order. So mu 5 can still be defined at low order. And the power of mu 5 can be understood by parity. So so this is just one feature. And this result agrees with that you derive from Kubo's formula. So this is just pure theoretical computation. And so this confirms that this result
Excuse
is
me,
credible.
so I do not see C, right? C is hidden somewhere?
C goes like E squared, proportional to E squared. So E is said to be 1.
Oh,
Yeah.
E is said to be 1. But, okay.
We can recover it, it's proportional to 1 power of C. Yeah.
So I could not see the fake theory in which C, I mean, without anomaly. Now, I hope that I could see, without anomaly, you get all these coefficients
To be 0.
But
Right.
that is not possible, right? Because you are dealing with the real theory, the correct theory. So everything comes out right, but I could not see the effect of the so-called anomaly, right?
Yeah. Yeah, I have to think about it.
Okay.
Whether one can demonstrate
So
this.
what is T? Capital
Temperature?
T?
Temperature?
Temperature.
Chemical potential? I'm going to give you some intuitive understanding of those effects. For example, the CB says that if you apply an external B field to the system, then there will be a current driven in the same direction. Usually the current will be driven by external E field, but here it's B field. So what's going on? When we have massless fermions, then helicity to a good approximation is conserved. So spin and momentum is locked. For example, when I have a left-handed particle, then this is the spin direction. It goes, it's aligned by the external B field, and the momentum direction for a left-handed particle goes this way. And for a right-handed particle, then the spin direction also goes with the B field, but momentum goes this way. So if I have the same number of left-handed and right-handed fermions, then the momentum will go in opposite directions, but of the same side, so the effect will be cancelled. So I need non-zero mu 5. Then you can ask, what if I set the chemical potential to be 0? So there is a symmetry between particle and antiparticle, and you can see that the effect does not disappear from those kind of simple arguments. I won't go through this, but I want to assure you